Okay, in this video, we're going to be doing the first part of the fifth assignment from my Calc CD class. We're going to evaluate the iterated or just double integral. And our integrand is going to look like h of xy is f of x times g of y. So we can separate it out into two functions that are just being multiplied together. One is a function of x, one is a function of y. We're going to integrate over rectangles. And let's take a look at the first one. So number 19, we're going from 1 to 3, then 0 to 2, x cubed y dy dx. All right, so I look at this and I think we have x cubed, and then that's its own thing. When we're integrating with respect to y, x is a constant, right? So we can actually factor that out. That's like if we just had 2y dy, we could factor the 2 out of the integral. So I can actually factor it out of this first integral, which will give me something that looks like this. So 1 to 3 x cubed, and then here we'll have the integral from 0 to 2 of y dy dx. But now, in terms of dx, if x is a variable, the integral from 0 to 2 of y dy is a constant, and so I can factor that out. So I'm going to factor this thing out. So this is why this works, and then after this, I'm just going to do the problems. So we have this. We have the integral from 0 to 2 of y dy times the integral from 1 to 3 of x cubed dx. This is like Calc 1 now, so I'm going to just kind of blow through it a little, right? So plus 1 times the reciprocal, and then we're going from 0 to 2. And then plus 1 times the reciprocal, so 1/4 x to the 4th, going from 1 to 3. And then we evaluate. So when you plug in 2, you get 4. When you plug in 0, you get 0. And then 1/4, when you plug in 3, you get 3 to the 4th, which is 81, minus 1. And you can simplify this to just 2 times 20, which is 40. Now, there's another way to do this where you don't ever make the observation and you just do the problem. Totally fine. So what you could do is you could look at this and say, the first integral that I should do is really with respect to y, because dy is the inner differential. So just do it, right? So we'll have 1 to 3 x cubed. And now I'm going to actually integrate the y term, so it's going to give me 1/2 y squared. And now I'm going to go from y equals 0 to y equals 2. I definitely encourage you, when you integrate with respect to y, when you're writing the bounds, write y equals and y equals. When you integrate with respect to x, and you write the bounds, only if it's the inner integral. When you're done, it's the final integral, you don't have to worry about this. But if there's still two variables involved, I think it's really helpful to label what the bounds are. So these are clearly y values that I'm going to sub in. Y is 0, y is 2, and then we'll still have a dx. And then you just kind of, do the math. So here we're using fundamental theorem, so we get this, which will give us this, and then we can integrate this to get this, and finally you get the same answer either way, which makes sense because you should if you're doing it right. Okay, so the next bunch I'm going to go much more quickly, I think, because I'm not going to explain the logic. I'm just going to look at it, identify that it's a function of x times a function of y, split it, and then do the problem. So here I'm actually going to do this one in basically the exact same way. So this problem, from what I can tell, is exactly the same problem. I don't know. These are just problems from the book, so you do them. Oh, I know what it is. This problem, let me bounce back. This problem that we did, number 19, was dy dx, right? So first y, then x. This next problem is first x and then y. But I was having trouble figuring that out because I'm just going to use that property and turn this into the exact same problem again, right? So this is what I would have done on 19 if I wasn't trying to explain it. I would have just immediately split it into the product of these two integrals, and then we've already done the work for this. So there you go. We get the same answer. So most of them are going to be like this in this section. Actually, all of them are going to be like this, but I'm going to choose to do them sometimes in different ways. So let's look at 21. So let's say that you don't really see this property, you don't notice it, or this one looks a little weird because there isn't an x or a y, so you're unsure maybe. You can just do them, right? So you keep the outer integral, evaluate the inner integral, right? We're going to integrate 1 with respect to x, which gives us x, and we're going from x is -3 to x is 8. So that's what I'm saying. For the inner integral, I think a best practice idea is to label the variable that you're subbing in for. It's a little more work, but wouldn't you rather get it right? So then this will be the integral from 4 to 9 of 8 minus -3. Not really sure how much work you all want me to show on these. This is definitely a Calc 1 integral, So I think you could probably do it without seeing all this work. So let's bounce through this. So integrate 11 with respect to y gives you 11y. Plug in 9, plug in 4, so you get 11 times 5. You get 55. All right, let's take a look at the next one. We're going from -4 to -1, 4 to 8, -5, and then dx dy. So what I'm going to do is I'm going to say that -5 isn't really an x or a y. It's actually just a constant. I'm going to factor it out of the first integral, and then it's a constant for the second integral. I'm going to factor it out of that. So overall, I'm just going to factor it out. And then I'm going to split this into, so I'll have -5. I'm going to have the integral from -4 to -1 of just 1 dy times the integral from 4 to 8 of just 1 dx. And now we're just going to do these. So -5, integrate this, you get y from -4 to -1, and then you get x from 4 to 8. So in this case, I don't think you need to say like x equals 4 to x equals 8 because it's not ambiguous. Like there's only one variable in the expression that you're applying the fundamental theorem to at that point. So I wouldn't show that step. All right, so then we actually do the work. Plug in -1, so you get -1 minus -4, and then you get 8 minus 4. And that's going to give you -5 times 3 times 4, which is -60. All right. So I'm trying to balance as I do these, like showing the work versus explaining, versus boring you out of your mind, versus having this video be 1,000 hours long. It's not an easy balance to strike, but I'm trying. All right, -1 to 1, 0 to pi, x squared sine of y dy dx. You'll notice throughout the video that I'm color coding. Everything with x is like that blue color. Everything with y is that, like, I don't know, yellowish, white, beige color. I don't know what color that is. That makes it a little easier. So like when you're reading the problems, it won't look like that if it was just typed up. You could do this if you are willing to use two different things. It takes forever to keep changing back and forth between the colors. But I think when you're learning and trying to understand, super helpful. So I'm going to split this because it's x squared times sine of y. It's just a function of x times a function of y. Split it into the two different integrals and multiply them. So we're going to get -1 to 1 of x squared dx times 0 to pi of sine of y dy. And at this point, it's just two normal Calc 1 integrals. So we integrate x squared, we get 1/3 x cubed from -1 to 1. We integrate sine, we get negative cosine from 0 to pi. Then we apply the fundamental theorem. So plug in 1, plug in -1, plug in pi, plug in 0. Use parentheses to be really careful and make sure you're distributing signs correctly. So cosine of pi is 0. No, it isn't. Cosine of pi, sorry. Cosine of pi is -1. Cosine of 0 is 1. So we have -1 and then minus -1. So we have 1 plus 1. And then obviously 1 minus -1 is 2. So this will ultimately give us 2/3 and then 1 plus 1. So we get 4/3 for this. Another good problem. All right, let's take a look at the next one. We're going -1 to 1, 0 to pi, x squared sine of y dx dy. So we've again like switched we switched the bounds, right? On the previous problem, number 23, y was going from 0 to pi and x was going -1 to 1. On this one, x is going from 0 to pi and y is going from -1 to 1. So as I'm a dyslexic person, I get confused by this all the time. Like I have trouble seeing the difference between the two problems. If they weren't consecutive, I wouldn't have a problem. But because they're consecutive, I'm like, why is this the exact same problem? It's not. We've switched the bounds. All right, but still, it's just a function of x times a function of y. So let's split it. And then we're going to integrate. So let's actually do that. So sine integrates to negative cosine from -1 to 1. X squared goes 1/3 x cubed from 0 to pi. And then we evaluate this. We get this times, that's weird, right? You go pi cubed over 3. But the negative cosine of 1, you have negative cosine of 1 minus negative cosine of -1. But the cosine of -1 is the same as the cosine of 1 because cosine is an even function. So you really just have negative cosine of 1 plus cosine of 1, which is 0, times whatever gives you 0. Could you have known this ahead of time? You could have, because if you look at kind of the first step where I split it into two integrals, sine is an odd function, and you're integrating it on symmetric bounds. So you're integrating sine from -1 to 1. If you integrate it an odd function on symmetric bounds, you are going to get 0. So we could have known going into it that this was 0 and like skipped pretty much all of the work. But that's one of those things that I tend to notice after the fact rather than like, oh, I know what I'm doing. All right, let's look at the next one. We're going from 2 to 6, 1 to 4, x squared dx dy. So this one you can split up into integral from 2 to 6 of 1 dy times the integral from 1 to 4 of x squared dx. But I'm just going to dive in and do it because it's not like super complicated. And also I think a lot of people do this without kind of thinking. So we would go 2 to 6. I'm just going to integrate x squared. So I'm doing the inside integral. So 1/3 x cubed from 1 to 4. I am saying that x is 1 and x is 4 because technically it's the inner integral. And there still could be other variables. And I like to just do the same thing every time, basically. I don't want to like think about it. So this will give me 2 to 6, 1/3 of 64 minus 1, which is 63 over 3, which is 21. So really we just have the integral from 2 to 6 of 21 dy, which gives us 21y from 2 to 6, which gives us 21 times 6 minus 2, so 21 times 4 is 84. All right, let's take a look at one more in this particular type. So the problem set moves on, but this is the last of this type, so it'll be the last in this video. We're going from 2 to 6, 1 to 4, y squared dx dy. This one I'm going to split. Why am I going to split it? I don't really know. Because you can think of it as two functions being multiplied. Y squared is a function of y, and 1 is a function of x. So we can actually just split this up into two integrals. We'll go 2 to 6 of y squared dy, and then we'll go 1 to 4 of 1 dx. So I'd like to emphasize, though, this is only working because our bounds are not dependent upon any variable. So we're integrating over a rectangle, and we can always write these integrands as f of x times g of y. If either of those things is untrue, we won't be able to do this, and we're going to see that in like the next part of the problems. But let's finish this. So this will be 1/3 y cubed from 2 to 6, and then it'll be x from 1 to 4. So 6 cubed is 216, I'm pretty sure. So 216 minus 8, and then we'll have 4 minus 1. So we have 208 over 3 times 3. So 1/3 of 208 times 3. I don't know why I'm making you watch this. So 208. Okay, so I'm going to stop this video here because the next set of problems looks a little bit different, but I hope this was helpful, and good luck.